Hello everyone. So in the last lecture we have discussed about different phase transformations. We talked about diffusional and diffusionless transformations, and we also talked about another classification, first order and second order phase transformation. So in today's class we will continue these discussions, and we will see the relation of this phase transformation with Rankine-Hugenoid curve. So as we know that the shock wave loading is of very limited time, so that's why this thermodynamic equilibrium is not possible because of the short time. So non-equilibrium processes are important here. However, we will assume we will treat the equilibrium processes in this discussion. So we will see a first order transformation, and with a PV isotherm, pressure volume isotherm, that means at constant temperature. So we have V volume in the x-axis and P pressure in the y-axis. So we are drawing a phase transformation, that isotherm, on a PV plane. So the isotherm will look like something like this. So here so this constant pressure zone V1 V2, so these are the volumes that, so this pressure is corresponding to PT, we can write this is transformation pressure. So that is the pressure at which the transformation will occur, and this range of volume V1 to V2, two phases coexist. Two phases will coexist in this range of volume. That means in V1 to V1, in V1 to V2 volume. So this is, I will write it, this is a pressure volume isotherm. This curve is, so this is what we are talking is not due to shock loading, but any general phase transformation on this PV diagram. Whatever we saw here is the phase transformation process. Phase transformation process that is for delta V smaller than 0. That means in this phase transformation process the volume will decrease with the transformation. So now in case of shock loading, so we do not have the isotherm. Shock loading, we do not have the isotherm, so I would like no isotherm, because the temperature will change, and so we need to develop, we need to plot the Rankine-Hugenoid curve for this shock loading. Rankine-Hugenoid curve. So we will see how to draw that. So what we will do is we will try with the earlier, whatever in the previous slide we saw, that pressure volume diagram. So this is in a three-dimensional plot, pressure on this axis, volume in this axis, and then we have temperature in another axis. Let's say T temperature in another axis. So if you draw these isotherms, so the isotherm. There are several isotherms we can draw. So this is one isotherm. You can understand this is the same as what we did in the earlier plots. Suppose this is I am drawing here again. So we have drawn that this is one isotherm for a phase transformation. So in this case we are drawing this at, let's say, at temperature T1. So this is isotherm because at constant, that means at constant temperature. Then at T2 we can draw another one. So we will draw another one, T2, and so similarly at T3. So this T3 we will draw. T3 is higher than T2. We can draw these isotherms. So here T2 is higher than T1. Sorry, T3 is higher than T2 and T2 is higher than T1. So that means our T is increasing this way, and that is obvious. You can see from, as I have already shown, this T is T axis in this direction, and now this two-phase region is this one. So so this is our two-phase region. So the two phases coexist in that region. So these are all isotherms. These are isotherms. If you remember the earlier lecture, so we have shown that the Clausius-Clapeyron equation or relation, we have seen that dP by dt is equal to delta S by change in enthalpy divided by change in the volume. So here in this case, as we in the earlier slide we talked about, this has a negative volume change, volume will decrease, and this is the first case we are talking about. So we will show another case. So in this case, so what we are assuming that the volume will decrease, anyway the phase transformation volume will decrease, and that entropy will also decrease. So if volume also decrease and entropy decreases, then dP by dt term will increase. That means the transformation pressure will increase with temperature. So this means the transformation pressure will increase. I will write this arrow with increase in temperature, or we simply write with temperature. So here in this case you can see that because temperature is increasing in this direction, and you can see that the transformation pressure, which is in this diagram, it may be little complicated for you, but if you see this, the pressure correspond to these this part is for the isotherm at temperature T1. So this is the pressure. So this is P1, and then if you see the second isotherm, the pressure is P2, and even in the third isotherm you can see that the pressure P3. So what we found here, the transformation pressure increases, that is, or we can write it as PT1. Similarly we can write, because the transformation pressure, so that way also we can write the PT1, PT2 and PT3. Probably that will be it make it clearer. So whatever we because that's a transformation pressure, not any other pressure. So Now we wanted to talk about the Rankine-Hugenoid curve. So as we already discussed that for shock loading we don't need isotherm. So no isotherm, that means we don't need isotherm, we need Rankine-Hugenoid curve. So how to draw the Rankine-Hugenoid curve? So it is little different than this isotherm. This point is actually there, we can draw a line here for the reference line where the this isotherm starts from. So now that's the a different line, but now we want to draw this Rankine-Hugenoid curve, which will go something like this. This Rankine-Hugenoid curve, it's difficult to understand from this, but anyways we will, in the next slide I will show you. Just you need to understand that this is not on a single PV plane like our this earlier the isotherm. So it will go something like this. So that means the temperature will change. So it may be little difficult to understand in this case. So in the next slide we'll have a simpler curve, and this Rankine-Hugenoid curve I will write RH. Curve is an adiabat, it's not an isotherm. Adiabat represents adiabatic process, and this curve can be determined from isothermal compression curve from by means of Grunet equation that we have already found that in an earlier lecture. So by means of Grunet equation. So Grunet equation is something like, if you remember, P minus pressure at 0 Kelvin absolute 0 equal to Grunet constant divided by V with internal energy E minus internal energy at absolute 0. So this is the Grunet equation, or actually this is the equation of state, we can call this is Grunet equation of state. From there we can determine the Rankine-Hugenoid curve. So we will see in a 2D plot which will be easier for us to visualize. So the earlier plot was complicated because we have even temperature axis, and so now here we have in a simple PV plot the same case, same adiabat here, or we can call Rankine-Hugenoid curve, or even it is known as shock adiabat because it's a adiabatic process. Shock adiabat on a PV plane. So first we will draw this the isotherm what we got in the earlier curve. So this isotherm, whatever we found in the earlier slides. So this is the isotherm. As we know, the mixed phase zone is V2 and V1, that is both the phases will exist. Now if you want to draw the adiabat will look something like this. So this dashed line is the isotherm, that means at its a constant temperature process, and this is the adiabat, or we can call shock adiabat, that is the Rankine-Hugenoid curve. And now we can see, it may not be very clear from this diagram, but there will be discontinuity in this point. You can see that this curve is not continuous like our earlier curve. So what in an earlier lectures, when we did study about shock wave, we saw that the pressure versus specific volume or volume, we got a curve like this, and that is we call the Rankine-Hugenoid curve for a for shock loading. So now in this curve, whatever we are drawing here is the same one, but we with a discontinuity. So this discontinuity exists because of the phase transformation. So this discontinuity, will represent or will this indicate onset of phase transformation. I will write within bracket discontinuity onset of phase transformation. So the phase transformation will start from here and till the volume V2. So after that the region and in between V1 and V2 will be two phase region. Two phase will coexist. So and probably higher pressure we will get a again one single phase, and both right hand side of this two phase region and the left hand side of the two phase region we will have a single phase, but in this V1 to V2 we will get a mixed phase. So this you should understand that this is on simple PV plane, but the earlier one was with PV plane, in the third axis is the temperature axis. So that's where we found some difficulty to show you the this thick RH curve. So that was, we found it difficult, but in this case here it is look very simple. And so the same case we have that was as we discussed, that there is a case 1 where the volume will decrease and also the entropy will decrease, and that gives us the pressure will, the transformation pressure will increase with temperature. So we will try to see the second case. The another case is case 2, where again we will have volume, negative volume change because for this phase transformation, but the entropy change is positive here, and that gives us dp dt is smaller than 0 from Clausius Clapeyron equation. So this dp by dt will be smaller than 0. So very quickly I will draw, even if it is not very clear. You can follow the textbook for this diagram. So and this is pressure, volume in this direction, and the third direction is temperature. So we will draw the isotherms. It will look something like this, and then the second one, second isotherm will look something like this, and the third one again not different, they all are same, and we have this mixed phase or two phase region here. So this is two phase region, and so and if you can see that in this case that transformation pressure decreases, or I'll just write PT, transformation pressure will decrease with temperature. That means if we increase the temperature, the transformation pressure will decrease. Here we can see that that let's say T2 T1 T0 this direction. So in increasing T is in this direction, and when the temperature is increased, if you see the transformation pressure P T2 P T1 and then P T0. So when T1 T2 T increases, that means here in this case actually sorry, we cannot write it here. So when T increases, that means he in this case T2 T1 T0. So and then the pressure will decrease. So PT2 PT1 PT0. So actually with transformation the temperature will decrease. So the transformation is happening when temperature will decrease. I'll write it here. Temperature will decrease. In this case, in the second case, decrease with transformation. And probably in this case we the completion will happen at T0 temperature. The phase transformation will be completed at T0 temperature. So you can see that T is increasing this way, but the transformation is happening in the opposite way, and T0 is the lowest temperature, and the transformation will complete. Sorry, I did not write completed. Transformation completed at T0. This case can be again in a simpler PV plane. We can draw like our previous case. So in this case what will happen, first we will draw the isotherm dashed line. This is our isotherm, and we will have the idea that Rankine-Hugenoit adiabate will look something like this. So in this case there will be two discontinuities. One second discontinuity is there. This is, as you can understand, that we are drawing the Rankine-Hugenoit curve, and in the first case we are showing the isotherms. Here mostly these are isotherm. In the Rankine-Hugenoit curve probably it is difficult for us to draw in the first diagram, then we are showing it here, and we can see that there are two discontinuities. That is the difference with the first case where our entropy change is negative. In this case the entropy change is positive, and that gives us the transformation pressure will decrease with temperature. And this is important to mention that this second case is less common. Second case is less common than the first one. Second case means delta S greater than 0 is less common than the first case. Which is, as you can understand, delta S is smaller than 0. So now you will check how this Rankine curve influences the shape of a shock wave, how RH curve influences shape of shock wave. So for that we need to draw shock front of two waves. So what we will do is we'll draw a shock front of two waves. The wave 1, we will write these wave as S1, or you can just say this wave is S1, shock wave 1, and this wave is S2, the shock wave 2. And if you see that shock wave velocity is us1, and in the second case shock wave velocity is us2, and if you know that this is basically a x versus distance versus pressure plot. These are the fronts, the first front, and there is another shock wave which is following the first one at a high pressure wave, that is us2, and we know that the material ahead of this will have pressure that should be 0, and also volume V0, and then we know there will be particle velocity associated with it. This particle velocity in the first behind the first shock wave, that this is the shock front, and the behind the first shock front is up1 and similarly in the behind the second wave, the wave velocity particle velocity is up2, and then we can say that in between these shock wave S1 and S2, this area will have pressure P1, volume V1, and in this area pressure P2, volume V2. And also we can see that the release wave can be drawn like this. So we'll probably discuss later about these release waves. So this part I will draw an arrow from here and we'll write release wave. We know what is release wave, we discussed earlier. And so basically we are dealing with now two shock waves, S1 and S2, and we should understand that the material in this region has a velocity up1, that is the up1 is the velocity, particle velocity. So for this for first shock wave, the relative velocity with respect to the material of this part is relative velocity will be us1 minus up1. So this is, we can write shock wave velocity with respect to the material between shock front S1 and S2. So, and similarly what we can do is the velocity again with respect to this material of the second shock wave will be us2 minus up1. So these are the relative velocities. What we can do is now is we can remember these earlier equations or earlier from earlier classes. So what we had is in a PV plot, or pressure versus specific volume plot. So what we discussed is this Rankine-Hugenoid curve, and then we found that for a particular pressure, so if we take the slope, this is we call the Rayleigh line. So this is Rayleigh line, and this one is our the Hugenoid curve, Hugenoid. So the slope of this Rayleigh line is important to us. We earlier saw this. So suppose P minus P naught, as you know, the P is the pressure at behind the shock wave, and P naught is the head of the shock wave. So similarly, V by V naught so is let's say in this case you can take pressure, this pressure P, or you can write P1 even, or V1 here. So this means P1 by V, P1 minus P naught, V1 minus V naught, that will give you the slope, and which is equal to rho naught initial density multiplied by shock wave velocity square, US square. And from this slope, and we have even we can say that US1 UP naught square is equal to what we can get that for this case. What we are doing is US1 minus UP naught, that's the ahead of the shock wave UP naught, and then V naught square is nothing but the V naught is the 1 by rho naught, the volume and density relation. So this will be P1 minus P naught divided by V naught minus V1. If you can understand from here that this minus sign comes because we are writing here V naught minus V1 instead of V1 minus V naught. So again, from mass conservation, this is also we discussed in earlier lectures. So mass conservation, which the equation was rho naught US is equal to rho US UP. Please revise these from earlier lectures. So from this mass conservation also we can have a for our problem, today's problem, so we can write this expression V1 minus V naught US1 UP naught. So you can understand that V1 V naught we are writing in place of rho naught and rho, which is thus just inverse of it. So from these two relations we'll write this as A and write this one as B. So similarly in case this is we are writing in terms of the points 1 and naught, like US1 and minus UP naught. Similarly we can write other equations with respect to US2 minus UP1 similar to A, V1 square P2 minus P1, the slope of this curve V1 V2, this we will and then another equation which is similar to B, the earlier in the earlier slide, US2 UP2, which comes from the mass conservation V2 V1 US2 minus UP1. So let's assume this is as okay, better we can write this all in 1 2 3 4, or maybe I will write 1 2 3 4. That will be will better give us better make it the picture more clear. So this will be 3, this will be 4. Then from 1 and 2 from 1 and 3, what we can find is, please go through this if it doesn't look very clear to you. There are simple calculations it seems, and otherwise refer to the textbook. So US1 UP naught divided by V naught square, and then if you see number equation, the expression number 2 and 4, from there we can have P2 minus P1 V2 minus V1 is equal to minus US2 UP1 divided by V1 whole square. So this is number 5 and this is number 6. If we substitute 2 in 5, that will give us P1 minus P naught divided by V1 minus V naught is equal to minus US1 UP1 divided by V1. So why we are doing that? Because we want to have this in terms of US minus UP1. So our relations will be US minus UP1. So equation number 7 is, we have in terms of US minus UP1 this equation, and even equation number 6 we have in terms of US2 minus UP1, which we needed for this problem. So we will see now this problem in the previous slide. So what is happening here is, the first shock wave is traveling at a speed of US1, but as we told that shock wave velocity with respect to the material is US1 minus UP1, and in the second second wave relative velocity is US2 minus UP1. So if the two phases to be stable, that condition for stability of the two shock waves or two shock wave fronts is that US2 minus UP1 should be smaller than UP1. So why so? Because if that is the case, the first wave travels always ahead of the second wave. But so what I wrote in this slide is, this should be US1 UP1 should be greater than US2 minus UP1. Okay, so if it's not greater than the other one, then what will happen? The second wave will overtake the first wave. Or that means there will be only one single wave. Two waves will not exist. That means two waves stability will not be there. Only single wave will exist if this condition doesn't satisfy. So this is the condition for stability of the two shock waves. So what we can do is, we can give it a number 8. So now you will see from number 6, number 7 and number 8, the condition will be P2 minus P1 divided by V2 minus V1 should be greater than P1 minus P naught divided by V1 minus V naught. So that is the condition. That is the condition for two shock wave structure. If that doesn't satisfy, that means the second shock wave will overtake the first, or that means Now it will be only one shock wave instead of two. So with that, so we are closing for today. So we have discussed about pressure volume isotherm and shock Hugenoid curve for corresponding to phase transformation, that is shock induced phase transformation. So what I discussed about the two shock wave structures. So you can see here we have shown two shock wave structures, and although I wrote it here, so what is the how the RH curve influences the shape of the shock wave. Sorry, but we did not discuss much about it. I somehow actually missed that point, and but anyways, you don't need to worry about it, because this will be covered in the next class. So what you understand now is the first is the two shock wave structures, and then we will discuss in the next lecture, so how these two shock wave structure is related to the phase transformation, that means shock induced phase transformation. So that's all for today. Thank you.